All right, let's take a look here at example 3. We have, let R be the region bounded by the curve f of x is equal to x plus 1, the quantity squared, the x-axis, and the lines x equals 0 and x equals 2. Find the volume of solid of revolution obtained by revolving R about the x-axis. Okay, so here we are. R is the region bounded by f of x is equal to 1 plus x, the quantity squared, the x-axis, and the lines x equals 0 and x equals 2. We are charged with finding the volume of R about the x-axis, right? Okay, now, as we know from forever ago, right? If you have a vertical line, that's x equals some number. And that's what we have here, is this vertical line where my x equals some number. All right? So, let's do this thing. I'm going to just wing this because I'm only concerned, and I'm not going to try to make some specific little graph here. I know that I'm going here from 0 that we have up to 2. So I'm just going to make this a 2. All right, so from 0 to 2, that's where we are bounded by here, right? 0 to 2. So if I know this is going on, I know that my function here is going to be 1 plus x, that quantity squared. So it's going to be the parabola, but it's such a tight little spot there for that parabola that I'm going to take a look at this here and I'm going to say, oh, let's just change the color. My function is going to be, so it's going to be moving to the left one, right? So let's say it's just coming out just from here to here. We're just winging it. That's what's happening here. This is my y-axis. This is my x-axis. Okay, so here I have this graph. And so if I take this graph and I swing this about the axis, then we're going to say that this is going to happen, about like this. That's kind of symmetric. Not real good. Let me try one more time. Kind of. It's close enough. All right. This is out here at 2. Okay. So that is what's happening, and I'm swinging this thing around, right? So I have this solid of revolution that's coming back through here because I'm swinging this around that axis. All right. So let's do this thing. I know that I now have circular slices. If I have a circular slice, then we're going back to that volume formula. I'm going to go from A to B of pi and then r squared. And r here is my f of x. And this is going to be with x as my variable. Set it up. So my volume here, I'm going to take this pi, you guys. Pi is just a number. Don't get wigged out by that. Pi is just a number. 3.14159, all that business, right? It's just a number. And remember, if you have that constant and just that number, you can chuck that thing in front of your integrand. So I'm going to put that in front because I don't really want to mess with it. And here I see from my problem, I'm going to go from 0 to 2. And then my function, which is going to be that radius here, right? My radius is coming up here to my function, and my function is 1 plus x, the quantity squared. Well, I am squaring that function. That is my function, and I am squaring that. Now I'm going to let that soak up. You see that? Okay. So my function is this. That's what goes in place of the f of x. That's what's in here. And then it is my function that is squared. So this is the function, and that's why I have the brackets here, and that's what's squared. All right? Now, power to a power you multiply. So let's make this happen, Captain. I'm When it goes 0 to 2, I really have 1 plus x to the 4th dx. Now, I'm not about to go through and take that to the 4th. We now have tools at our disposal when it comes to integrating. If you have that inside function there, don't get crazy on that. Do a little u sub. U is going to be my 1 plus x because that's my inside function. Then my du here is just going to be dx. When you sub to a u, make the full conversion. If you change the variables, you have to change the bounds because it all goes together. So at x is equal to 2, that should be a t, and it doesn't look like it even a little bit. At x is equal to 2, when I plug a 2 in here, 2 plus 1 is 3. At x is equal to 0, u is 1. So those are my new bounds. Now, I have my volume is equal to pi, and I'm going from 1 to 3 of u to the 4th du. Now we can integrate that little beauty all day long, right? So let's do it. I've got pi. If I add 1 to that, I've got 1/5 u to the 5th, and I'm taking that little fella from 1 to 3. So I've got pi over 5, and I'm just going to keep that in front because I don't want to mess with it. I've got 3 to the 5th minus 1 to the 5th. 3 to the 5th. Well, let's think about it here for a second. I've got pi over 5. So I know 3 to the 4th is 81 times 3 is 243 then, right? So I've got 243 minus 1. So 243 minus 1 is 242. So my volume is 242 pi's over 5. And I don't have a specific unit here, so I'm not going to worry about putting a unit on this. And we're just going to leave this in terms of pi. I don't expect you to be able to pull that off and figure that out from there. All right. Not bad, right? You were literally only using the formula of a circle. That's it. That's it. Right? Pretty cool. Pretty cool indeed. Good. Do you see how important it is to be able to recognize a U sub, execute that U sub, because it's no longer about learning how to integrate. That expectation is already there. The new expectation is, can you put forth the how to do it? Can you apply it to this type of problem? Right? So integration is now just a tool in your toolbox. Now can you apply it to this problem so that you can work it out? Good. Good, good.